All right, so we are into chapter 4 now in elementary calculus. We're looking at section 2, which is about finding the derivatives of products and quotients. And there was a problem in the previous section where I said, there's a faster way to do this, a better way. But I told you to go ahead and FOIL out a product of a couple of binomials. And in this section, we're not going to have to do that anymore. And we're going to talk about it right away. So this is the first little subtopic I want to talk about here is the product rule. And we can't distribute the derivative over a product. What you're seeing in this sort of tan colored box is the product rule. And it says I've got to get my pen out so that I can actually be writing while I'm talking. Here we go. It says that if we're taking the derivative of a product, that's equivalent to taking our first factor and multiplying it by the derivative of the second factor, and then adding the second factor times the derivative of the first. This is maybe a more consolidated way to write that. I don't know why we're writing it with F's and S's instead of U's and V's. I think maybe a better way to write this would be to say that this is equal to U times V prime plus V times U prime. Or if you want to keep the U's and the V's in the same order, you could write it as U times V prime plus U prime times V. Whichever one of those is going to work best for you, pick it, write it into your notes, and stick with it. As long as you've got the derivative of both and the originals of both mixed together with a plus sign between them, you're in good shape. And then let's have a look at this example problem. We want to use the product rule to find the derivative of the function. So I'm going to write this as f prime of x equals, I'm going to keep the first factor of 4x minus 4. And then we'll multiply that by the derivative of the second factor, 5x plus 1 prime plus, and then I'm going to take the derivative of the first factor, 4x minus 4, I'll put the prime on that one, and multiply it by 5x plus 1 without the prime. Now let's go in and actually take some derivatives. The 4x minus 4 is staying the same. We're taking the derivative of our second factor. The derivative of 5x is just 5. It's a line. 5x is a line with a slope of 5, so its rate of change, its first derivative is 5 all the way along. The derivative of a constant value is 0 because it's a horizontal line with a slope of 0 all the way across, plus the derivative of the 4x minus 4 is 4 minus 0 effectively because the derivative of that constant value is 0. So that is just a 4 times the second factor of 5x plus 1. So if I lost you at all on taking either of those derivatives, you need to go back to the previous video and make sure that you're comfortable with taking the derivatives of polynomials, the derivative of constant values, exponent times the leading coefficient, decrease the exponent by 1. That's the rhythm. Go back, get the rhythm, and then rejoin us. From here, it is distributing and combining like terms. So let's distribute 20x minus 20 plus 20x plus 4, and then we'll combine like terms. We've got a total of 40x's. Minus 20 and plus 4 is negative 16, and that is the first derivative. If you want to check and make sure that it's correct, go ahead and FOIL this out. Combine like terms, and then take the derivative. You're going to get the same thing. So the product rule, that's nice. I like that. Instead of having to FOIL and combine like terms and then take the derivative, I can just do it right away. Here you use the same process. You apply the product rule, then distribute, then combine like terms, and then the question is to write an equation of the line, of the tangent line to the graph at the point on the graph where x equals 0. Let's go ahead and do this one. I will do it without quite as much narration. So I'm going to take the derivative of my first term, which is 4x plus 3, and then I'm going to keep my second factor, negative 4x plus 1, plus I'll keep my first factor, 2x squared plus 3x minus 2, take the derivative of my second factor, which is just negative 4. Yep, just negative 4. I forgot to put the plus 1 in here, so let's make sure that that gets in there. Yep, that looks good. Okay, now let's distribute. In the beginning of this process, we are still going to have to FOIL, even though we're in the throes of the product rule. We actually implemented the product rule already. That's what we did in our first step, and now we will start expanding this, and then we'll clean it up by combining like terms. So here I'm going to FOIL. And then in this next term, I'm going to distribute from the right. I'm happy with that. Okay, then let's combine like terms. Let's look at our x squared terms first. I've only got one of them. It's a negative 8x squared. Then let's look at our x to the first terms. I've got negative 16x, and then I'm going to add 4, which makes negative 12x, and then I'm going to take away 12x, which makes negative 24x, and then another 12x away from that, which makes negative 36x. And then our constant values, we've got a positive 3 and a positive 8, which makes for plus 11. And then we want to write an equation of the tangent line at the point on the graph where x equals 0. Reminder, in order to write the equation of a line, we're going to use point-slope form, which means we need a point and a slope. Let's find the slope first. M is going to equal f prime of 0, because we were told to plug in an x value of 0. That's when we're finding the tangent line. And that's equal to negative 8 times 0 squared minus 36 times 0 plus 11, which equals 11. So our slope is going to be 11, and now we need a point. The point on our original function is the point where x equals 0. We need the corresponding y value. So let's go into our original function f, plug in the 0, and that is 2 times 0 squared plus 3 times 0 minus 2 times negative 4 times 0 plus 1, which is negative 2 times positive 1, which equals negative 2, which means that x1 comma y1 is, we plugged in an x value of 0, we got out a corresponding y value of negative 2, so this is the point that we're going to be plugging into point-slope form, and that's a go for point-slope form. So that is y minus y1 equals m times x minus x1. Let's plug in our values. Y minus y1 was a negative 2 equals our slope m, which is 11, times x minus our x1 value, which is a 0. And then we clean this up a little bit, and it turns into y plus 2 equals 11x. At this point, we might as well turn it into y equals mx plus b form, which is slope-intercept form. Let's subtract 2 from both sides so that we have ourselves a y equals equation of y equals 11x minus 2. And that is the equation of the line that is tangent to the original function at the point where x equals 0. I'm pretending like I can hear applause. Okay, let's keep going. The next subtopic, and the only other subtopic for this section, is the quotient rule. So we just looked at an instance where we had parentheses times parentheses, in other words, two expressions multiplied by each other. Here we've got u divided by v. So it's the quotient of two expressions or two functions. Not as pretty, okay? V is in the denominator, u is in the numerator. So we've got our denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. Yes, you have to commit that to memory. That's not going to be on a formula sheet or a cheat sheet or anything like that. So this you need to know. I used to struggle remembering this, and a technique, sort of a mnemonic that somebody shared with me once that sticks a lot better than the denominator times the derivative of the numerator minus the numerator. Forget it. Never going to remember it. Maybe you could remember it better in terms of u's and v's. V times u prime minus u times v prime over v squared. Well, that's much shorter. I liked this description. If this is what you're taking the derivative of high over low, then the result is low, the denominator, times the derivative of high minus high times the derivative of low all over low squared, which is the same thing as low times low, which means that the quotient rule is low d high minus high d low all over low low. Depends on what you're into, I suppose, but if that has a better rhythm to it, then use that. If you want to do it in terms of u's and v's, use that. If you like it written all the way out, the derivative of a quotient is the numerator times the derivative the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. Super. Have at it. I'm going to pass on that. I'm going with high over low, personally. Use the quotient rule to find the derivative of this expression. You can absolutely do this. Or if you wanted to chop this up, distribute the division, sort out your exponents, and take the derivative of that using normal properties of derivatives, that would be great too. But since we're here to practice the quotient rule, let's practice the quotient rule, and then we'll pop down and look at an applied problem. All right, so y prime equals the denominator, low, times the derivative of the numerator, minus the numerator, high, times the derivative of the denominator, d low, low d high minus high d low. So I need the derivative of the denominator. The derivative with respect to x of the square root of x is the same as taking the derivative with respect to x of x to the 1/2 power. In order to take the derivative of x to the 1/2 power, we take the existing exponent, multiply it by the coefficient, which is a 1 in this case. So 1/2 times 1 is 1/2. Keep the variable, decrease the exponent by 1. 1/2 minus 1 is negative 1/2. And so that is d low. All divided by the denominator squared, which is the square root of x squared, which is going to turn into just an x. And now we have the extreme pleasure of distributing and combining like terms and then dealing with the division. If I sound about as excited as you feel, you're correct. I'm right there with you. However, having the opportunity to study not just math, but the other things that you're studying perhaps is a luxury, and so we should be very grateful that we have this opportunity. And speaking of opportunities, I'm going to take this opportunity to change this into x to the 1/2 power. It's going to make it much easier to distribute it. Whether you want to erase it and change it to an x to the 1/2, or you just want to keep it in your mind that that's what we're doing, or put yourself a little note maybe. Square root of x equals x to the 1/2 power. That way, when we start distributing, dist, when we start distributing, we get, in the numerator, 2 times x to the 3/2. This is x to the 2/2, and this is x to the 1/2. And when you add those together, you get 3/2, plus 8 times x to the 1/2, minus, and now I'm distributing over here also, right? Doing my distribution here, coming in at it from the right, distributing, distributing, distributing. We get minus 1/2 x to the 3/2 minus 4x to the 1/2 minus 3/2 x to the negative 1/2. Let's double check our work. This is positive, this is positive, this is positive, this is positive. But this is negative, which means they're all going to become negative. When we distribute to here, and to here, and to here, we're going to have 3 terms, and they're all going to be negative. 1 negative term, 2 negative terms, 3 negative terms. So far, so good. But put that back, okay? So they're all going to be negative, so I'm done with that. Now let's look at coefficients. Coefficient of 1, positive 8, positive 3, positive 1/2. 1/2 times 1 makes 1/2. 1/2 times 8 makes 4. 1/2 times 3 makes 3/2. They're all still negative. Yet again, still doing well. Let's look at the variables. I've got x to the 2 times x to the negative 1/2. 2 minus 1/2 is 3/2. Winning. X to the 1 times x to the negative 1/2. 1 minus 1/2 makes 1/2. I love it. This is x to the 0 in here after the 3 times x to the negative 1/2. 0 minus 1/2, negative 1/2. I love it. Just love it. All right, so we're in good shape, and we're going to take this entire thing and we're going to divide it by x. Let's try to combine like terms in the numerator. Let's look for our biggest exponent first. I don't see any x squareds, so x to the 3/2 is our next largest exponent. I see 2 of them here, and we're taking away 1/2 of an x to the 3/2 power here. And that's it. Okay, so I've got 2 of them, take away a half of 1. That leaves us with 3 halves of an x to the 3 halves power. Then let's look at our next largest exponent, which is x to the 1/2. Here's 8 of those, and we're taking away 4 of them, which leaves us with 4, positive 4, x's to the 1/2 power. And lastly, we have a minus 3 halves x to the negative 1/2 power, and all of that is still being divided by x. When you're dividing by x like this, make sure that you distribute your division. So the division has to happen here, and it has to happen here, and here. That's pretty. And since you're dividing by x to the first power, that means you can do the upper exponent minus the lower exponent. For example, 3 halves minus 1 will equal 1/2. So this equals 3 halves as the coefficient, variable, new exponent, 3 halves minus 1. Plus, coefficient stays the same, variable stays the same. Exponent of 1/2 minus exponent of 1 makes negative 1/2. Coefficient comes down, negative 3 halves. Variable is still x. Previous exponent was negative 1/2 minus 1 makes a new exponent of negative 3 halves. This is one possible way to express your final answer. If it was requested that we express our final answer without any negative exponents, we would write it up like this. So the x to the 1/2 is appearing in the denominator there, minus the 3 is in the numerator, the 2 is in the denominator, and now the x to the positive 3 halves is also in the denominator. That's another way to write it up without negative exponents. If the request was for you to express your final answer using radicals instead of exponents, your final answer would be 3 halves times the square root of x plus 4 over the square root of x minus 3 over 2 times the square root of x to the third. Note, how should I write this? The square root of x to the third is equal to the square root of x squared times the square root of x to the 1. The square root of x squared, of course, is technically it's the absolute value of x, but I'm going to write it just as x times the square root of x. Could you be requested to write this version of the final answer with a common denominator? Yes. Do I have any interest in doing that with you right now? No. You're sad, I'm sure. However, not doing it. But you could do it. Your common denominator would be the square root of x to the third, or x root x. And then our applied example is about average cost, or another little subtopic, I suppose, is about average cost. The average cost per item is calculated by taking the total cost of all of the items that you are producing and dividing by the number of items. So average cost equals cost to produce X items divided by however many items. The rate of change of average cost. In other words, marginal average cost. Rate of change, marginal derivative. We would need to take the derivative of the average cost function. So marginal average cost. Similarly, marginal average revenue and marginal average profit. You would have to take the revenue or profit, average revenue or average profit, and take the first derivative. In example 4, our last example, we're being told that the total cost to produce X units of perfume is this. We want to know the marginal average cost. Before we can do the marginal part, we're going to need the average part, which means we will need to take our C function and divide it by X. So the average cost is equal to the cost function divided by the number of items, which is 2x plus 5 times 6x plus 4, excuse me, all divided by x. And then the marginal average cost function is the first derivative of this. Now, in this expression right here, in the numerator you have a product, and in the denominator, well, there's a denominator. Since you've got a product in the numerator, it sounds like we're going to need to use the product rule up there. And since this whole thing is a fraction, it seems like we're going to need to use the quotient rule. Also, it's a twofer. That is not the most efficient way to do this. The most efficient way to do this is to FOIL the numerator, distribute the division by the denominator, and then take the derivative. Could we use the product and the quotient rule? Absolutely. The quotient rule, which is the overarching rule that we would use because this whole thing is a fraction, would tell us to, so maybe don't write this down yet. The average cost function turns into the marginal average cost function when we take the derivative of it.